Okay. Good evening, everyone. Welcome you all. Uh, so, we are in this course on programming data structures and algorithms using Python. And this is our last week and the last session. And hope you all have watched all the lectures from the first week to the eighth week. Uh, Today, we'll be going slightly uh, understanding what happened in week 8, and we'll also try to uh, cover up everything that we discussed till week 8. Some of you might have joined. I think on Sunday we had a revision session. We tried to recollect things. I asked a few questions, and you guys tried to answer that. So some of you told that you need more of those kind of questions. So uh, we'll do that as well, so that it will be helpful for you to recollect things, whatever has been taught till now in the course. So yeah, so this course is instructed by Professor Madhavan Mukund, as you all know. So he's from Chennai Mathematical Institute, and uh, this is like week 8, as I told, and I am your DA Syed Shabir Ahmad, and I'm from Department of Applied Mechanics and Biomedical Engineering, I think that. So let's go about this. Okay. So how many of you took this course last year as well, or before? Uh, like, is anybody there who has taken this course already and like trying to give the exam again, like re-attending the exam again? So all of you are like fresh. Uh, yeah, fresh. Uh, yeah, yeah. Sorry, sorry. Krish Sharma, you. Krish, you want to say something, or is it just you have turned on the mic? Okay. It's like as I asked, if any of you have already taken this course, let's say last year or last semester, and like trying to uh, give the exam again, is there anybody? Okay, Vidya, you are not. You are fresh. Yeah, you are a fresh student for this course. Okay, okay. Shashank, you were trying to say something.
Yes, sir, I am fresh. Sir. I registered for that course last year, sir, but I didn't attend the exam, sir.
Okay, okay, fine. Okay, okay, okay. I just wanted to ask, like, if somebody already gave the exam, so that we could get you guys some idea about how the exam will be. Because I tried to get some previous year questions from the NPTEL team. They told we'll not be able to share. They have some policy that they won't share previous year questions. So I tried, but I couldn't get. Okay, like you have to revise with whatever you have. There are a lot of questions available here and online as well, so you can try going with that. So yeah, so in week 8, we discussed a few things about recursion and dynamic programming, and like how uh, memory allocation and aspects of these aspects in Python. So first, we saw what is recursion. So recursion is basically we are solving a problem where the solution depends on the smaller instances of the same problem. Uh, like we can think of it as a breaking a large task into slightly smaller tasks until the task is so simple that it can be solved immediately, and then you take all the smaller tasks and pile it up to get the final solution. So that's what we did, right? So for a recursive algorithm to work correctly, there are basically uh, two things. It must have two parts. One is the base case. So we all know this. So the condition under which the function stops calling itself. So that prevents the infinite loops, which we discussed. Like without this base case, like it will be running infinitely. And then there is a recursive step. So the part of the function that reduces the problem into smaller parts or reduces the problem size and calls itself. So let's say you want to find the factorial of n. So we know that it is nothing but n into n minus 1 into n minus 2 up to n. So up to 1. So you can see that we can write 5 factorial as 5 into 4 factorial. So this is an overlapping structure. So we can write the factorial of n as this. So if n is less than or equal to 0, we return 1. So this is our base case. So which is saying that 0 factorial is 1. And also if numbers go below 0, uh, there is no such thing called factorial. So we'll just return 1. So make sure that like if you are getting like if your input is a negative number, so it will return 1. So if n is a negative number, then also it will return 1, apart from being 0 factorial as well. So this is the base case, and if your n is not equal to 0 and if it is greater than 0, what happens is that it will go to this else clause, which is n into factorial of n minus 1. So you can see factorial function is calling itself. So this is a recursive step. So while calling this, like you can see, it will factorial of n minus 1 when it calls. So this n will become n minus 1, and it will check again if this is the base case, if n minus 1 is the base case. And if it is not, then it will go to the else clause again. Then it will be n minus 1 into n minus 2 factorial. So it will go on doing this recursive step. It will be going on to implementing this. It will be implementing this recursive step until it will hit the base case. So that is what it will happen. So while doing this, a recursive evaluation of the factorial function. So you can see there is a trap in this. So there are a lot of overlapping subproblems. We'll see what are those. So it is like it looks elegant, right? Like you are calling the function. Uh, function is calling itself. It looks very elegant, and it seems like we have reduced lines of codes, number of lines of code to be written. But there are some traps as well. Like it can be very slow as well. So let's say you have this thing, right? Like where we to get the Fibonacci sequence uh, of numbers. So in this example, so each number is basically sum of two preceding ones, right? So basically we'll start with 0 and 1, then 0 plus 1 is 1, and then 1 plus 1 is 2, and then 1 plus 2 is 3, and then 2 plus 3 is 5. Like that, this series will go on. So each number is sum of two preceding ones. So this is the function, right? So Fibonacci of n, like if you want to calculate n Fibonacci like uh, numbers, then what you'll do, like 5 sequences you want to get. To do that, then we write this function. So like if you give input n, so it will check if it is n is equals to 0 or n is equals to 1. So then it is just basically 0 and 1. Then if it is not, like if n is not equal to 1, then it will take uh, Fibonacci of n minus 1 plus fib of n minus 2. So this is how it will do. So like that, you can see there is some inefficiency here. So like if you want to get Fibonacci of 5, so you can see it will be Fibonacci of 4 and Fibonacci of 3, right? So then it will be breaking down into Fibonacci of 3 and Fibonacci of 2, and again 3 into Fibonacci of 2 and 1, and then similarly it is Fibonacci of 1 and 0. So like that, again Fibonacci of 2 is 190. So here you can see this f of 3 and f of 2, here we calculate here, but again we have to calculate uh, these again here as well. So repeated, like multiple times we are evaluating the same function. So this recursive call will make that happen. Because of the writing this recursive call, we have to make the same calculation again and again because of this structure which we have written. So this is a problem, right? Like if I have already calculated f of 3 and f of 2, so why is it like again it uh, needed to spend time, computational resources on calculating the thing which we have already calculated again and again? So it is just waste of time and waste of memory. So you can see that because of this three kind of structure which it is occurring, so this problem will take like exponential time. You can see it will take 2 power of n. So the order of efficiency, uh, computational complexity is 2 to the power of n. So we already discussed that this is a very bad computational complexity. We already saw this in our, I think, search algorithm. So it is like not efficient at all. So we have to make it like the efficiency should be either it should be order of n or a order of n log n or order of log n. So that is like yeah, I'll share with you. I'll share the this file in the Google Drive. Okay, so you can see. So here basically making the algorithm like worse by writing this recursive call. So the computer does a massive amount of wasteful recomputation. So that is what we are seeing from this algorithm which we have defined, or like the function which we have written, recursive function. So there is a solution to it. So that is like that can be given to you by memoization. It is not memorization, it is memoization. So there is no R here. Memo means like kind of a record or a table. So like you have a memo, like a book kind of where you write things, right? So that kind of thing. So memoization and dynamic program. So there are, these are two different things, but both will help us improve our efficiency of the algorithm. So to solve this overlapping subproblem trap by giving the computer a memory. So you tell the computer, okay, if something is calculated, you store it, because if we need it in the future, we will take it from your memory and use that instead of recalculating again. So that is what we want to do here. So if we have computed a value once, we will save it. So that's what we will do in memoization. So memoization is a top-down approach of programming. So like kind of a dynamic program, but like not completely dynamic program. So so it will keep the recursive structure, like it will keep the same recursive structure, whatever we have discussed, but it will add a dictionary or a list uh, to act as a lookup table. So in this table, all the steps, all the calculations which we have done will be stored. So if you require it in the future, then you will look up in the table and get it from there instead of like repeatedly again evaluating the same stuff. So this is the extra stuff, extra thing, right? So this was already there. So this was already there in our function in the Fibonacci base case and the recursive computation. In addition to that, we are putting this if clause in which we will see if n is in the fifth table, which means like if you have already calculated a Fibonacci of let's say n, then you will receive then you will return fifth table of n. So this answer is nothing but this comment which has come here. So ignore it. So this is this like comment, but it has come to the next one. So you don't care about that. But after this line, this is the line. Okay. So first, if n is not there in the fifth table, like whatever the dictionary or the memory in which you are like storing the computed stuff, then it will go. If it is the base case, then it will give the value n. If it is not the base case, then it will give the value again it will do the recursive computation. Okay. So after doing the recursive computation, whatever the value which you get here or here, you will save that in the table. So if that is already saved in the table, like here f of 2 and f of 3 you are computing, and f of all these things f of 4, so these things will be saved in the table. So now again you require f of 2 and f of 3, right? So then you will not require to do the computation again. So this recursive call will not be required uh, to do the calculations again. So it will, if n minus 2 is already there, if n minus 2 is already there in the fifth table, it will catch here itself and it will return you the value. So that is the uh, uh, approach which we'll follow in memorization. Okay. So again, same thing. It will go from here to here. So you can see it is going. This is a top-down approach. So it will go from. It will take 5. It will divide it into f of 5, f of 4, then f of 4, f of again into f of 3 and f of 2. So till it will hit the base case, right? But the only thing which we are avoiding is like here, if I have done the calculation for f of 2 and f of 3, I won't do it again. So I will share these values in the table. So whenever again, if I require f of 2 and f of 3, so this will be called up from the table, and we will save the computational resource. So that's what we are doing here. Okay. So the second way of doing improving the efficiency is dynamic programming. So in dynamic programming, instead of starting at n, like we started at f of 5, right? So instead of doing that, what we do is and do like going using the recursive approach from going from n to 0. So in dynamic programming we will say that let's start at 0, like we will start at 0 and we'll like build our way up to n. So we'll start from 0 1 and 0 plus 1 to 2, so like that it will build up to n. Iteratively we'll do that. So this avoids recursion entirely. So there is no recursive call here. So you will just use iterations, and we will use an array to store the dependencies, whatever which we get here, like array or a list. So identify the base cases. So we have to get the like first we have to identify the base cases, and then we'll put them in the table. Like 0 and 1 are our base cases, we'll put them. So here you can see this is the dynamic programming approach. Using that, we have written the function to calculate the uh, Fibonacci. So here, if n is equals to 0, it will be 0, right? So sum is 0. So if then if n is not equal to 0, then it will be 0 plus 0 into n minus n plus 1. So these are the base cases. In the fifth table, first you will save this. So 0 into n plus 1 means like it will say, let's say if you have uh, because how many, let's say if we have given 5 here, so then it will share, then it will save 6 zeros in the table. So 0 into this list of 0 into n plus 1 is 0 into 6. It will share a small list with 6 zeros. So then we have this pip table base case, which is 0, and pip table 1, which is equal to 1. And then we will fill that table, right? So whatever the table which we have. So firstly, we will start with uh, 2, like because 0 and 1 are already there. So first index and sorry, the 0th index and first index is already there. That is the base case. Then we will start with fifth table 2, which is fifth table I minus 1 plus fifth table I minus 2, which is fifth table of 1 and 0. So like that, it will go from 2 to how much? 6, because we have given n, right? So we want to go till 6. So then we will return the table whatever which we are getting. So now you can see here, because there is no recursive call here, there is only table which we have defined, if table, and we are not calling the function in itself. We are not doing any of this. We are going from 0 to n, like like how we do in general, right? Like how we calculate the Fibonacci sequence. 0 and 1 will be there. 0 plus 1 is 1, 1 plus 2, 1 plus 1 is 2, 2 plus 2, 3 is 5. Like that, we will do here. So this is dynamic programming. So here again you can see there is like we are not doing any recomputations, and we are just saving a table, and from that we are getting, right? So both memorization and dynamic programming will help reduce the computational complexity from 0 to order of 2 to the power n down to order of n. So it is like a massive reduction uh, in the computational time. So you will save a lot of computational resources. You won't be doing recomputations. So the algorithms will also be faster. Okay. So then we also saw this grid path problem. So basically, you want to go from here to here, and you can go either right or either left. So that's what we dealt with. Like we wanted to know how many ways we can go from here to here. So this is nothing but you imagine that there are like these are roads. You can assume that there are roads. Like a city has a grid-like structure. Roads have a grid. Roads are in a grid-like structure. You want to go from this point to this point. Okay, and in order to do that, you can go either right or either top, but you cannot go like down, and you cannot go left. So you we just take this table, like and use this grid path formula, which is basically like from here to here. If I go, like I can go here to here only in one way, right? Like I can just take right, and here to here also. From here to here, from here to here, I can go only in one path. I can go only in right, like only taking right, because I cannot go top and I cannot go come. I cannot come again down. So this is only like here to here you can only go in one way, and also here to here you can only go in one way, that is going in the top. But here to here you can go here, like from here to here you can go like this, and right, and like let's say you can go from here, like we want to go from here to this point to this point. We can go like this, or we can go like this. So there are basically two ways in which you can go. So that's why like you have to take this and this, like bottom cell and the left cell, whatever the values are there. You already these are the base cases. Like you should fill them by default, because you can go only in one way. and there is only one path to go from here to here, all this thing. Then, but if you want to go from this point to this point, then we can go like this, or we can go like this. So this is simply you can compute by using what is there in the left cell and what is there in the bottom cell. Uh, you just add them and you can compute. So similarly, if you want to calculate this, then you can calculate how many ways in how many paths you can take to reach from here to here. You can take this 2 and this, it will be 3. So then finally here it will be 3 and here also it will be 2 plus 1, this will be 3. So then finally uh, from here to here, let's say you want to go, so that we can calculate by 3 plus 3, like it will be 6. So in 6 ways you can travel from this point to this point. So this is a DP logic for the grid path problem. So basically we, as I said, we will just build the tables. So we will start from 0 and we'll go till the top, like till end. So unlike recursive function, like defining a recursive function where we go from top to bottom, so this is a more efficient approach. So in the grid path problem we also have holes, like if there is a hole, like if there is some obstruction here, like we cannot travel, so that is also there. If that is blocked, so any part trying to that hole is invalid. So you have to keep here, like if you cannot, you have to basically fill those paths with 0. So like if you cannot go here, it should be filled here 0. So like that we take care of blocked paths. So that's how we can solve this grid path problem. Like if you want more, like you can go again, rewatch the lecture. But yeah, so this is how we can use dynamic programming to solve this grid path problem. Then we have also longest common subword, right? So you want to calculate longest common subword. Here it is sec, right? Here it is yes sec. T is not there, so here this and this are like longest common subwords in bisect and secret. So to do that, we can write a logic such that uh, 1 plus like if this of u, and like if the second element in the string of u and in the zeroth element in the string of v become equal, then we can say we have one common letter, and then we will go and look for more letters, right? Then we will add one, so we go diagonally. So we do that. So like that you can build a table like this to solve this problem. So this is secret and this is bisect, right? So and we'll also have one empty cell in the end. So we'll start from t. So t and t are common. So you will say okay, one is like common. So then you will go diagonally. You we don't have e and c as common, so it will be 0. Then again we will see here and here wherever there are common stuff is there, like you will just uh, keep it as 1. Then you go diagonally and check if the diagonal things like e and e again are common. So it will be 1. So yes, c and e are both common letters, so it will be 2 words are common. So then again we'll go diagonally here from e to s and s. So s and s are common. So basically this is how we'll build a DP table for our problem. So this has a logic. So you have to implement. So first you have to initialize the grid. Okay, like lists of list in Python. Basically, single list means you can just say as a row, but because this is a 2D grid, in a list you will have again multiple list. So basically it has m plus 1 cross n plus 1 filled with zeros initially. So the extra row and column like this plus 1 and plus 1 is, and it will act just as a base case. So then we will create a variable, and we will traverse backwards. So we'll start from back of the word, and we'll go like this. Okay. So this is how we have an outer loop and an inner loop. So this is the basic coding logic you have to follow. You have to remember this. Like if you are not like let's say if you know the algorithm very well, you can write this logic by on your own. But if you don't know, but you like then you have to learn this algorithm, like how you can write step by step. Using this logic, you can basically write this Python function. So this is the logic which is followed. So whenever you write a code, you should write like this. Step by step, you have to write the steps, and then you write the code. So this is how we uh, get the longest common subword. Okay. Similarly, there is also this longest common subsequence, right? So like subsequence means like there is no need of continuity. Like we have this, right? So like S, E, C, and also T is there. So it is a sequence, but it is not like continuous, but both are in secret SEC, and in the end after R and T, it is T is there. Bisect is there, so SECT. So both have subsequent, although not continuous, like you can say. But so to do that, we'll start from here. So we'll go diagonally. T and T are matching. Again diagonally, it is not matching. So we'll check here and here. We'll go on the right. So there is a logic to this, that we have to common subsequence, right? So if you and like you will check diagonally if things are there matching. If it is not matching, then you take the max of I plus 1 comma j and I comma j plus 1. So this is I plus 1 comma j, and this is I minus 1 comma j. So using that, we can do this traversing in the table, and here again we'll find from here to here we'll go, and here again we'll find C and C are matching. So we'll take 2 and 2, and we'll go till here. So there are 4 words in the subsequence that are matching, and using this, like you can write this code, the logic which is there. Using this, you can write the code. So basically, inside the loop, what happens if it is matching? Take the value from the diagonal and add 1. That's what we are doing. If there is no match, you are allowed to skip. Take the highest value between the cell directly below or directly to the right. So that take the highest value. It is not matching. Take the highest value directly below or directly to the right. So like that, we will build all the cells in this table. So this is how we code, and yeah. There are things like I will share this. You can read how to recover the string. To do that as well, we can write another function, but it's not okay. Then we also had a matrix multiplication, right? So matrix multiplication also can become very expensive process if you don't do it properly. Like let's say you have multiplication of A, B, and C. So matrix multiplication is associative, which means basically it will satisfy this property. So A into B C A into BC can is equals to AB into C. So in order, like you can say that both will give the same result. There is no difference. in the multiplication, either you do like this or like this, but there is a difference. Like how, in order, like the order in which you multiply will drastically reduce the computational steps. Like if you do, like we have these matrices with these sizes 1 cross 100, 100 cross 1, and 1 cross 100, right? So if we do A into BC, which is basically, so uh, BC has a 100, let's say 1 and 1 is common, right? So BC will give you 100 cross 1 into 100. So there will be 1000, 10,000 operations. Then you do A into BC, it will give you another 10,000 operations. So totally it will take 20,000 operations to do A into BC. Whereas if you do AB multiplication first, it will give basically 1 into 100, 1 into 1, which is basically 100 computations. Then again, it will be, AB will be a 1 cross 1 matrix, and this C is 1 cross 100. So it will take again 100 computations. So basically, it will take 200 computations to do the same multiplication of AB into C. Instead of doing like this, if we do like this, we will see like how many thousand times we are like, not thousand times, 100 times we are reducing the number of computations. So we can take care of this by again doing the dynamic programming. So you can read about this. Like if you want to find the best place to split. So here, if you are splitting here, you can see it is taking 20,000. Then if you are splitting here, you can see if you are splitting after the second matrix, then it will take less number of computations, right? So first we will calculate in which splitting how many computations it will take by using this logic. Uh, Cost is nothing but how many computations it will take. Hello, I can hear it. Where's my mouse? So just give me a second. Just give me some time. Okay, we'll do one thing. I'll just restart. There is some. I'll stay connected, but I'll just restart my system.